Thank you. Thank you very much for the introduction, and thank you very much to the organizers for inviting me to this gathering of very wise people. Today I'm going to talk about this idea of trying to extract some information from basic geometric quantities about the gravitational field strength. Now, this is a work that is based on a collaboration with Ted Jacobson and Anthony Speranza. And this is the reference. And this is the outline of my talk. So I will introduce some geodesic balls, and then I will just compute very, very simple things, area of the boundary of the ball, and then I will try to find a connection with the definition of quasi-local energy. Now, the main idea behind my talk is very, very elementary. We all know that GR, general relativity, tells us that the gravitational field is the geometry, is the curvature of the space-time. So a very basic question is, how does this curvature affect the basic geometrical quantities, that is length, area, volume, and is there any relation between those and the strength of gravity? Now, this was answered years ago in 1921 by Pauli in his book on relativity. And you can also check this book, the Feynman lectures, where Feynman wrote what is written on the screen, the rule that Einstein gave us for the matter going to geometry is that if you have a region of space with matter and you take a very small sphere around it so that the density of matter can be considered to be constant, then the radius excess for the sphere is proportional to the mass inside the sphere. And actually, what you can quantify this using the definition of excess radius. I'm going to use this notation here. So this means variation of the radius at constant area. So keeping the area constant. So I'm going to keep all this notation in my talk. And then this is proportional to the mass. Or if you want, to this quantity here using the density of matter rho. So in this particular calculation, what you do is you keep the area fixed, and then you see what is the excess of radius to keep the area constant. Now, I am going to quantify this by doing some very basic calculations. Now, you choose any point P in your manifold, and then you choose a unique time-lag vector, U, at that point. And now what I'm going to do is I'm going to construct a ball, like a spherical ball. In Minkowski spacetime, it will be spherical by just sending space-like geodesics in all possible directions around P. And I'm going to do that using Riemann normal coordinates. So this is the meaning of this acronym, based at P, and such that the unique time-lag vector is just the zero coordinate. Now, this special geodesic ball you can prove if you throw space-like geodesics from the point P, which are originally or initially orthogonal to U, you can prove that these geodesics lie on the hypersurface x naught equals to 0. And actually, as we are using Riemann normal coordinates, the basic idea about the Riemann normal coordinates is that geodesics satisfy this very, very simple relation. They look like straight lines. So here R is the affine parameter, N is the vector initially tangent to the geodesic. Of course, we choose this vector to be space-like with respect to U, spatial with respect to U, and therefore we can have, that then has no zero component. Now, the notation I'm using is that Greek indices are space-type indices from 0 to 3, and Latin indices are space-like ones from 1 to 3. Now, as I said, R is the affine parameter, and of course, as N is originally a unit, this satisfies that. Now, all the tensors and things that you are going to see in this talk are all tensors at the point P, okay? Now, then what you get is something which we can represent here like a disk with a boundary, but in real space-time, it would be a ball with a boundary which is a two-sphere. And of course, the unit vector n at the point P can be described as a function of coordinates on the boundary, right? So if I use theta and phi as coordinates on the sphere, which is the boundary, the ny's will be just the traditional functions which make this to be satisfied. Sometimes these are called the direction cosine. So the typical sine theta, sine phi, sine theta, cos phi, and cos theta. Okay, in this way we have constructed a ball and a boundary which looks like a sphere. In flat space-time, there will be a true spherical ball and a real round sphere. Now, of course, if we are in a curved space-time, things are a little bit different. So I am going to define the ball, and I'm going to do a perturbation order by order. And at first order, I am going to use this perturbation, which I call delta L super 1. And of course, this I can split into two parts: the part which is spherically symmetric, or if you want the spin zero perturbation, and then the part which actually depends on theta and phi. Now, using this perturbation, you can compute at first order in the curvature using Riemann normal coordinates the area of the ball. And now the area of the ball is given by the flat area. So this means A flat. So this is 4 pi L squared, where L is the affine parameter that you get there except for the perturbation. And then this is equal to this thing. So this is the spherically symmetric part. And this calligraphic R is the intrinsic scalar curvature of the hypersurface at P. So this is the scalar curvature within the hypersurface at P. Now I'm going to use this notation. So this will be called the first variation of the area. A very simple formula. Now, as you can see, at first order in the curvature, this part does not contribute. So only the spin zero part, the spherical symmetric perturbation, does. This one. Let's see. Yeah. And then we can recover Feynman's interesting remark by keeping the area fixed, because if we keep the area fixed to the flat space-time value, then we get the formula for delta L1, just putting this to 0. And if you also use the constraint equations, so as we are using Riemann normal coordinates, the scalar curvature of the hypersurface is equal to 2 times the 0,0 component of the Einstein tensor. And if you also use Einstein field equations, then what you get is simply that at first order, the variation of the radius, which is this, if you keep the area constant, is proportional to G naught naught. If you use Einstein field equations, this is proportional to the energy momentum tensor time-like component. And then you can write this, which is what Feynman wrote. Now, we could do something else. We could alternatively keep the ball's radius fixed and see what is the deficit of the area. Now, if you do that, which in this case is the same as keeping the average radius fixed, the first variation of the area keeping the radius fixed is given again by something which is proportional to the energy momentum tensor. I mean, to the 0,0 component of the energy momentum tensor, or if you want, the energy density at the point. So both the radius excess, keeping the area constant, or the area deficit, keeping the radius constant, are both proportional to the energy density at the center of the ball. But they have a different proportionality. This is all very well, and as I said, it was already known many years ago. But now my question is, what happens if you are in vacuum? So what happens if the energy momentum tensor is 0 at the point? Of course, if the energy momentum tensor is 0, the radius excess and the area deficit both vanish at this order, first order in the curvature. However, we know that the gravitational field itself is a source of curvature. And this purely gravitational curvature also affects geometry and, of course, all the geometric quantities. So if we trust these relations between change in radius or area and energy density, the corresponding changes of radius, area, etc., at higher orders in the curvature should also be related, maybe, to the pure gravitational energy density. Or the other way around, maybe deficits in area or radius can provide a notion of quasi-local dimension. So we have to go to the next order in the Riemann normal coordinate expansion. And I am telling already that we are going to get some terms which are quadratic on the curve. Now, for that, then I'm going to need the electric and magnetic parts of the curvature. This is well known to most of us, I guess. Now, given that the Ricci tensor is 0, we know that the Riemann is purely Weyl tensor at the point P. And Weyl can be decomposed, given that we have the time lag unit vector U. It can be decomposed into its electric and magnetic parts. So this is the electric part, the 0I, 0J component. The magnetic part with epsilon is the Levi-Civita symbol on the hypersurface. And of course, we only need E and B because the remaining components of the Weyl tensor can be written in terms of the electric part like that. Here, H represents the metric on the hypersurface T equals 0. And at the point P, this is just the delta. So I'm going to use the E and B. And of course, you know that these are traceless and symmetric tensors. I am using them at the point P. Now, so now we are going to take the ball at second order. And of course, we have to do a perturbation to second order. Remember, we had this first order perturbation. This part did not contribute to the area at the first order. And then we are going to put the second order perturbation. And I'm going to split this into a spherically symmetric part and the part which depends on the direction. So this is what I'm saying here. This is just the spherically symmetric part, or if you want the spin 0 part. And these other parts, the delta tildes, depending on the point on the sphere, they can be expanded in spherical harmonics. So this is what I'm going to do. I take the delta tilde L1, this part here, and I expand this in spherical harmonics. This is just writing this expansion. I am not taking the S equals 0 part because this is already there. And these numbers here, these are totally symmetric and traceless things for S greater than 1. So this is the traditional spherical harmonic expansion. Now, if you compute the area of the balls now, and you assume that the Ricci tensor is 0, and of course that the first variation is also 0, because we want to keep first order to 0, then the difference of the area with the flat space area is given by that. Here I'm using B squared is just the square of the magnetic part, E squared the square of the electric part, and all these squares here are just the squares of these spherical harmonic components, if you want. As you can see, there is a part which depends on the Weyl tensor. There is this part which depends on the excess radius. This part which depends on purely on the deformation. And then there is this part which is very, very important. This is the coupling of the deformation with the gravitational field. And it only couples for spin 2. So this is a quadruple thing, okay? The only part of the deformation that couples to the gravitational field is the spin 2 part. This is why I put this in red. So at this order, we cannot aspire to fix these other parts because they do the same in flat space-time as in curved space-time. So this is what I'm saying here. The spin 2 deformation gives a different contribution than in flat space. And of course, if you take the set of space, the vector space of traceless and symmetric tensors at the point P of rank 2, this is a 5-dimensional space. And then you can write any tensor in terms of a basis. In other words, I can always write, given the electric part as data, I can only write the deformation, which is arbitrary, as something proportional to E plus a part which is orthogonal to E. Now this part, the Z part, does not contribute either to the area deficit. So it's only the part of Y which is aligned with the electric part of the Y tensor that gives a different contribution. So we can remove all the deformations for spin different from 2. We can also remove this Z part and just take Y aligned with E. And then the important thing is this coefficient gamma, which is just a number. Now, with this in mind, if we just use this deformation, only the spin 2 proportional to the electric part with gamma, and if we use the explicit value of this constant B that appear in the previous formula, this is what we get for the deficit of the area. I remind you that this is the flat area. Now, the magenta terms would be the variation at second order if we keep the radius fixed completely. Now, the red terms are the part which are due to the spin 2 deformation and its coupling with the gravitational field. Now, if we remove everything which is not in magenta, we get something which is negative different. And maybe we could think that this is a good quantity to define an energy density at this order. But the question is this a correct energy density? So we should know which kind of properties we want to give to the thing we are looking for. And I'm going to discuss this in a minute. Now, there are two possibilities here as before. I can keep the area constant, so I put this equals to 0, and then I get a value for delta L2, which is the spin 0 deformation at second order in terms of the B's and the E's. Otherwise, I can also keep the delta 2 equals to 0, radius fixed in average at second order, and see what happens to the area. This is what I'm writing here. If I keep the area fixed, so that at first order already this is 0, this is what I get for the variation of the excess of the radius. Gamma, I remind you, is the proportionality factor between Y and E. And I can also keep the average radius fixed. Only the average radius contributes at this order now. I can forget about the delta tilde L2. And this is what I get, which looks very similar with a different proportionality factor. Now, the question is, does any of these formulas contain something which is related to the gravitational strength, or if you want the gravitational energy density, quasi-local energy density? And if it is, if some of these formulas contain such a thing, what should we expect as the correct answer at this ordering vacuum? Now, let me give you what I think are the required properties that we need if we want to give a true physical meaning of energy density to any of these deficits or excesses. Now, the first thing, it should be positive definite, and it should vanish if and only if the Y tensor vanishes. We are keeping the Ricci tensor equals to 0 now. It should be quadratic in the curvature, that is in the Y tensor now. It should be the time-like component with respect to our time-like vector of a tensor field. Now, this is, of course, the case, always the case for an energy density. Now, the thing is now, what is this tensor field, the underlying tensor field? Now, this tensor field should have properties which ensure that the putative energy, the would-be energy, propagates causally, in the sense that if initially at any space-like region, this thing vanishes, then it should vanish in the entire domain of dependence of this initial region. And for this to happen, the underlying tensor field needs two important ingredients. The first one is some control on the divergence of the tensor field, which is in the usual cases, this is ensured by the underlying field equations if they are, for example, hyperbolic. And the second ingredient that you need is the dominant property. This is the generalization, if you want, of the dominant energy condition. This is the tensor has to be non-negative when you contract it with any number of future pointing vectors. I mean, with a number of indices. Now, if this dominant property is satisfied, then also the momentum, which is the tensor contracted with a time-like vector except on one index, points into the direction of the propagation of the would-be energy. Now, is there anything that satisfies all these properties? And there is a unique tensor that satisfies that properties. This is the Bell-Robinson tensor. So now I'm going to have a brief interlude just to remind people of what is the Bell-Robinson tensor. And for that, I'm using, for inspiration, the electromagnetic field. So if F is the Faraday tensor representing the electromagnetic field, the energy momentum tensor of the electromagnetic field is given by that. And this can also be written using duals, Hodge dual like that. The tensor is symmetric, it is traceless, it satisfies this quadratic important condition, which leads to the famous Rayleigh condition. It has the dominant property. For arbitrary energy momentum tensor, this is called the dominant energy condition. But for the electromagnetic field, this is a property. Okay, the electromagnetic field always satisfies this. So the tensor on any future pointing vectors is always non-negative. And if any of these vectors, I mean, if all these vectors are non-null, then this is strictly positive. Also, the divergence is like that. And of course, this leads to conservation in the covariant way if there are no charge or no currents in your area. And of course, this leads to conserved quantities if you have Killing vectors or conformal Killing vectors. So now, instead of using F, now I'm going to use the Weil tensor. And the thing that I can construct in a similar way is called the Bell-Robinson tensor. So this is the Bell-Robinson tensor in 4 dimensions. We can check that this is just similar to the previous formula. Now, remember that this could be rewritten using duals. And of course, this can also be done here. You can write this simply like that. So this is like the very same formula. This tensor is fully symmetric. It's also traceless. It also satisfies the quadratic condition. And it also has the dominant property, which is fundamental. Okay? If you contract this on any 4 future pointing vectors, this is always non-negative. And of course, if you are in vacuum, so if there's no matter around, this tensor is also divergence free if the Einstein equations hold. I mean, it reaches 0 or with lambda. And again, this provides conserved quantities with Killing vectors. So the Bell-Robinson tensor is somehow reminded us of energy momentum tensor, but it is not an energy momentum tensor, and it cannot be because there is nothing like local energy in the gravitational field. It looks somehow related to the energy momentum properties, but also its physical units are wrong because geometrically these are linked to the -4. The correct physical units for the Bell-Robinson tensor, you have to multiply by that, are energy density per unit area. Now, in any case, is there any relation with gravitational energy? And this was answered many, many years ago for the first time by Horowitz and Schmidt. What they did is they took the definition of the Hawking mass, but you can take any quasi-local definition that you like of energy. There are many in the literature. You take any quasi-local energy for a closed surface, and you apply this definition to a tiny sphere of radius L. Then, if you compute the energy, this quasi-local energy that you choose at first non-trivial order in the radius, this is what you get. So you see 4π/3 radius to the cube energy density. So this is what you expect for a very, very small sphere. But again, what happens if we are in vacuum? Then the energy momentum tensor is 0, then we have to go to higher order. At 4th order in the radius, there is nothing, so you have to go to 5th order. And as I said, as first proven by Horowitz and Schmidt, what you get at the first non-trivial order is the energy momentum tensor is 0, is the total time-like component of the Bell-Robinson tensor times L to the 5. And here there is a constant, excuse me, which depends on the particular quasi-local energy that you are choosing. So for the Hawking mass, this is 1/90, but for other quasi-local energies, this is different. So there is certainly a relation between quasi-local energy and energy momentum tensor for small spheres. Now, analogously, if you compute the gravitational momentum vector for a small sphere, this in non-vacuum leads to the T0I component of the energy momentum tensor, but if you are in vacuum, you get the T000I component of the Robinson tensor. Okay, so what is the totally time-like component of the Robinson tensor in terms of the electromagnetic part, where it's E squared plus B squared. So the previously computed formulas that I showed you can be rewritten using this notation now, like that. And this is a very appealing form, because you see we can get, in both cases, the Bell-Robinson time-like component if we choose gamma, which I remind you is the proportionality factor between the spin to deformation and the electric part, to be 1/12. So if we put gamma equals to be 1/12, this disappears, and we get just the Bell-Robinson super. Now, this value of gamma is magical. So setting gamma equals to 1/12 is just saying that the deformation I'm used is just the first order deformation, that it will be 0 in vacuum. Now the second order, plus a first order deformation, which is aligned with the electric part with 1/12 here. And then there is the second order perturbation, which is here. And this part, the part which is not the spin 0 at second order, will not contribute now. Now, the computation at first order gave us these two formulas. I showed you this before. And if we are in vacuum, this of course are 0 then this is what we get at second order. And you see, this is the excess of radius. This is the deficit of area at the corresponding order. They are proportional to the energy density, they are proportional to the Bell-Robinson tensor, and the relative factors in this case and this case agree. So one can say, okay, so then maybe this is a good definition for energy density. Now, what happens to the rest of variations? Because we have also only been concerned with area and radius. Now, if you compute, for example, the volume change and other things, the value 1/12 makes always the variation extreme. So it maximizes the excess radius if we keep the volume constant and so on. So there is this magic about 1/12, but of course this is not a nice thing to do. I mean, I do the calculation and I see, oh, I have to put gamma equals to 1/12 to get what I want. There should be an independent reason in telling me that gamma equals 1/12 is the good thing to be done. And this leads to the question, which are the balls we have to compare? Because we are comparing balls that we are constructing by doing these geodesic balls to things in flat space-time. Which balls are we to compare? I mean, which balls should we say they are the same to be compared? You see, at quadratic order in the curvature, given that if I am in an arbitrary point in my space-time, the gravitational field around these points is anisotropic, then the radius r will be different in various directions, right? But now, how to give a natural prescription that compares the round ball in flat space with something which now has different values of the affine parameter as the radius? And here there is an independent argument. We can compute again a geometric quantity. So we can take the boundary of the ball, which is two sphere, and then we can compute the trace of its second fundamental form. And if you do that at this order in perturbation, what you get, of course, is the flat space-time value, which is 2 over the radius, and then all this deformation, taking all the spin part into account. And you see, this is very, very nice, because if we want to keep the trace of the second fundamental form constant on the entire sphere, and also equal to its value at flat space-time, then we have to remove all the spin different from two deformations, which is what we did before, because they didn't do anything different than from flat space. And also, we have to kill this part, the spin 2, and this gives me precisely the 1/12. So K is constant on the entire boundary and equal to its flat space-time value if and only if all the spin different from 2 are 0, and the spin 2 deformation is aligned with the electric part with 1/12 as the factor. So this is an independent argument, nothing to do with area or with energy, just doing geometry. Okay, so this provides an intrinsic definition which is independent of the space-time of the boundary of the ball, which fixes precisely all the deformation to be 0 except for spin 2 with gamma equals 1/12. So I'm now going to my last slides. So recall, this is what we got at first order for the variation of the spherical symmetric variation of the radius, keeping the area constant, and the deficit of the area, keeping the radius constant. These were proportional to the energy momentum, and this is what we got at second order if the energy momentum tensor vanishes. Given that the proportionality, the relative factors are the same, then we can take this as my definition of energy, right? And then I would say that the energy, or if you want the mass, it depends what you prefer, is just take the variation of the radius, keeping the area constant, and just multiply by 3c4/g. Alternatively, you can say, and this is exactly the same definition, compute the deficit of the area, keeping the radius constant, and multiply by this factor. And this, both of these formulas are valid with matter and without matter. So at first order in the curvature and second order. Now, if you use this as a definition of the energy, this is what you get. So at first order, for the energy over c², or the mass, you get what we all want to get, 4π/3 rho radius to the cube. And if we are in vacuum, so density equals to 0, matter density, then what we get for the mass, or the energy over c² is this thing here. So this is the E² plus B², so the Bell-Robinson super energy density, reduced to the 5, and this factor. And observe that now I get this factor univocally fixed. So if I trust this calculation, this is the factor, 1/150. So I'm going to my conclusion now. Therefore, if you believe these calculations and you trust this relation between changes in geometric quantities and the strength of the gravitational field, and therefore energy density, this is what you have to do to get a quasi-local energy, including the pure gravitational one. So you choose any point in your manifold, and you choose there a unit time-like vector U. Then you build a tiny spatial two-sphere. So spatial meaning that is locally orthogonal to the time-like vector that we have chosen around the point P, and with a radius which is angle dependent. So it depends, the radius depends on the initial direction. And this radius is determined by the constancy of the trace of the second fundamental form. By the way, this is equivalent to keeping both null expansions of the boundary of this two-sphere equal to its value in flat space. Now, you do that, and this can be done in any space-time, and then you adjust the area to be that of the Euclidean round sphere with the radius L. And then, given that, you compute the excess radius in average of this surface with respect to L. Once you have done that, this gives you a number, and then you multiply by 3c⁴/g, and this would be the quasi-local energy relative to this observer time-like vector U at the point P in a very tiny sphere around P. So this is one way, and there is an alternative equivalent way, which is adjust the average radius of X of the surface to a fixed value L, and then compute the area deficit of the area of the surface of the sphere with respect to the Euclidean one. And then once you have this area deficit, you multiply it by this quantity here, and then you get the same. So this is a very nice and very elementary way of trying to deal with the non-localizability of the energy and trying to give a precise formula for the local or quasi-local pure gravitational energy. So this is what I wanted to say. Thank you very much for your attention.